So order of growth in ascending order, Tn equals O1, so that is constant growth. For example, array access, Tn equals O log n, that is binary search. Tn equals On, so that is linear growth. So for example, looping over all elements in one dimensional array, Tn equals On log n. So for example, merge sort, that is very important, merge sort. So the big O notation, the big O value of merge sort is O n log n. So Tn equals O n log n. So that is n log n growth, that is merge sort. So merge sort algorithm is very important. So you have to pay extra attention on merge sort. So for merge sort, it is n log n. And Tn equals On to the power k, that is polynomial growth. Tn equals O2 to the power n, that is exponential growth. So if you go to the big O examples, so I'm using the slides of MIT. Tn equals C1 n squared plus C2n in average case. So C1 n squared plus C2n is less than equal to C1 n squared plus C2 n squared. So which is also can be written as C1 plus C2 n squared for all n greater than 1. So let's see the definition. Tn equals O, T of n is in big O of f of n if and only if there are constants c and n0 such that T of n is less than or equal to c of f of n. So we are using the same thing. So we are looking at the example 2. Tn equals c1 n squared c2n in average case. So we are writing something which is, so we are writing c of f of n, c1 n squared c2 n squared, so that is c1 c2 n squared for all n greater than 1. Therefore Tn is in On squared by the definition. Tn is in On squared by the definition. So that is the upper bound according to the definition. In this example, finding value x in an array, so that is average cost, that is C is n divided by 2. So for all values we are applying the definition C is n divided by 2, C is less than equal to C is n. So therefore by definition Tn is in On for n0 equal 1 and C equals Cs. So the big O notation is Tn is in On. So remember we are getting the tightest one. So we can use On squared as well, but we are using in the same class as this. So we are using in the same class. So we are taking On. So here according to the definition we write it in the higher class. So the highest grade is n squared here, so we make all these things n squared. Therefore T of n is in On squared by the definition. So we can, you might think we can write n cube as well and so on, higher grades. Yes, we can write, but we take the one which is in the same class, the closest class of the highest grade. So that is n squared. So we take it in the closest class of the highest grade. So if we look at big O notation, so it is the upper bound. We can take n cube and all so on, but we are taking the tightest one. So according to the definition, it shows the tightest upper bound we are selecting. The tightest upper bound. So that is On squared. So example 3, if it's constant, we say it is O1. So watch this, we go examples carefully again and again. So we are looking at the upper bound, yes, but we are taking in the same class in the tightest case. So for example, C1n squared per C2n, so the highest grade is n squared, so we make all these things n squared according to the definition, and we take it On squared, so that is the tightest case. So we can make it n cube as well, that is also big O, but as per the rule we are taking the tightest one, so we can use On squared. So here the highest grade is n, so n divided by 2, so n is always greater than equal to n. So we are writing something here which is greater than or equal to n divided by 2, so that is n, and that is the tightest case with the n, so Tn is in On.